It's 2:58 Eastern Standard Time. The Cassini spacecraft has been watching the vortex near the North Pole of Saturn for years in infrared, but today is different. This is the first time since arriving at Saturn that the North Pole region will be lit by the sun. This means that for the first time, Cassini will image this vortex using visible light. When that image finally arrived at JPL in California, scientists were amazed. As one scientist puts it, we did a double take when we saw this vortex because it looks so much like a hurricane on Earth. But what's even more amazing is how this image was received from a transmitter 1.2 billion kilometers away that uses less than 60 watts of power by a receiver that was also moving. This amazing work is done by an array of radio antennas clustered in 3 locations on Earth. These antennas collectively form the Deep Space Network. After traveling 1.2 billion kilometers from Cassini in 1 hour and 20 minutes, our hurricane signal hits Earth. But before we can do anything with it, we need to make sure that our receiver is in the path of our signal. And remember, the Earth does rotate around its axis. Canberra, Goldstone, Madrid. These are the locations of the radio antennas of the Deep Space Network, or DSN. They are located in Australia, United States, and Spain respectively. With this setup, a DSN antenna located in at least one of these locations will be in line of sight of a spacecraft no matter where that spacecraft is in the sky. That's because the locations are separated 120 degrees apart. 120 times 3 gives us 360, which represents the entire celestial sphere. So no matter which part of the sky our signal arrives from, it will always fall onto at least one DSN antenna. It's nice. It's nice. After 1.2 billion kilometers, our signal will actually fall onto the detector. But that's not good enough to guarantee a strong signal for us to amplify for further processing. If we just amplify the signal with the regular antenna, we'd be receiving only a small amount of the energy from our signal, since the energy that generated our signal has now been spread out really thin over its 1.2 billion kilometer journey. So, the more we can recapture that spread out energy, the more we can make it stronger. And that's the function of the dish part of the dish antenna. The bigger the dish, the more expensive the food. Well, actually, it's the exact opposite, but seriously. The bigger the dish, the more energy from an incoming signal can be focused onto the detector. The more we can make our signal louder than the background noise. You may be wondering why the dish wouldn't also focus the background noise. Thing is, dish antennas are highly directional, and the amount of energy from a signal that can focus onto the detector depends on the direction of said signal relative to the dish. The more head-on the signal is, the more the energy is focused, or the higher the gain. That's why dish antennas are sometimes called high-gain antennas. Since some of the background noise will be coming from various directions, most of them won't be focused onto the detector. So it's a 2-punch kung fu move. The dish antenna amplifies our weak signal and ignores most of the background noise. Stay focused. We still have to get the signal to our amplifier. Our detector is located at the focal point of our dish antenna. This point is above the dish and in the center. Since we're dealing with a really low signal, we need to amplify the signal right at this point. If we instead send the signal via wires to the control room at the base of our antenna, the signal would lose strength and also noise will be picked up by the wires themselves, acting like antennas. In either case, the noise level relative to the signal would be increased, but placing a low noise amplifier at the focal point presents its own set of problems. 1. Maintenance. Because the low noise amplifier is located at the focal point, which is high above the ground, maintenance work must be carried out by a mobile crane or other specialized vehicles. 2. Weatherproof. Since the low noise amplifier is located outside an environment, it must be waterproof, withstand large temperature swings from day to night without performance being affected, and not deteriorate due to moisture in the air or UV rays from the sun. 3. Movement. The orientation of the low noise amplifier should not affect its performance. This may seem like an easy requirement to fulfill, but keep in mind that the high performance low noise amplifiers used at these sites are not small and often require a complex cooling system to minimize thermal noise. 4. Weight. The amplifier can't be too heavy because it makes construction more costly, because stronger structure has to be built on top of the dish to support the amplifier. Finally, 5. Size. The size of an amplifier has to be limited as to not interfere with the reception of incoming signal by the dish itself. So, as you can see, there are numerous problems with locating the low noise amplifier at the focal point. These issues are manageable for small dish antennas, but as the dish gets bigger and more sensitive, these issues become the limiting factor for dish size in cost-effective dish antennas. So the low noise amplifier was moved from the focal point on the outside to the control room on the inside. Since wires are very inefficient for transmitting really low signals, engineers had to come up with a more efficient way of getting the signal from the focal point to the low noise amplifier in the control room. The solution: beam waveguide antenna, or BWG antennas. Compared to a regular or so-called front-feed dish antenna, a BWG antenna has 3 additional mechanisms: the waveguide tube, waveguide reflectors, and subreflector. We'll start with the subreflector because it's located at the focal point, a location where the detector would sometimes be in a normal dish antenna. The subreflector is a concave-shaped structure coated with aluminum. The accuracy of the surface is 0.15 millimeter. That is to say, it deviates no more than 0.15 millimeter from the ideal shape. Now, that's tight. The job of the subreflector is to focus the beam from the dish into the beam waveguide. The beam waveguide is a collection of tubes that houses a series of reflectors to direct incoming radio waves from the subreflector to the detector. The main challenge for constructing this waveguide is that one part is attached to a dish which has 2 axes of freedom for rotation, and the other part is attached to a stationary room. Engineers solved this issue by dividing the waveguide tube into 3 sections. These sections are attached to each other via a joint that allows each section to rotate around its axis. You can see how this simple method of attachment allows the dish to rotate in one axis, the support structure in another, and the control room to remain stationary. Inside the waveguide tubes are 4 reflectors that direct the incoming beam to the detector. They are positioned in such a way that no matter how the dish and the assembly structure turns, the reflectors will stay within the same location relative to each other. Clever. DSN dishes uses both BWG and conventional dish antennas. So now, our signal can finally hit the detector and be amplified.
What is your message? Hello, who do you say you are?
The low noise amplifier used is not a solid-state amplifier. Instead, it's a maser. Maser is just like a laser, but instead uses microwave instead of light. That's why maser starts with an M instead of an L. The second letter, A, stands for amplification. So that's what we're using the maser for, microwave amplification. The entire maser setup is cooled with liquid helium or liquid nitrogen to a temperature of 15 Kelvin inside of a vacuum flask, commonly known as a Dewar flask. Depending on the setup, the liquid coolant may have to be replenished every so often because it evaporates away. After our signal has been amplified by the low noise maser amplifier, it's then downconverted from its 8 GHz frequency to a frequency between 500 to 1000 MHz. This is because the electronics in the next stage of processing cannot operate above 1000 MHz. This next stage is data acquisition. This is where the actual data is stripped from the carrier frequency. But before doing that, the signal is amplified a few more times. Remember, we're dealing with a really low signal here. Finally, after 1.2 billion kilometers of travel, our signal is recorded to disk or tape and then transmitted to JPL via conventional communication line and protocols such as SSH or FTP. Recording the data at the site of the receiving antenna is very important. The last thing you need is for the data to get corrupted while being transmitted directly to JPL, and you don't have a backup. So, for now, don't even expect a delayed feed from deep space. After JPL receives the image, it will eventually be transmitted to their web server, which will then transmit it to you. The amount of work that went into you receiving this image is simply amazing. The math, the science, the engineering. Let's not forget the finance guys. Yep, can't forget those guys. There are other DSN-like antennas located all around the globe. For example, the European Space Tracking Network has 12 dish antennas located around the globe. China, Russia, Japan, and India also operate similar networks. There's more to the DSN, and I hope to do a second video on it and talk about some of the scientific research that DSN performs using just radio wave. Until then, this is Dex D for the Celestial Sphere.